Okay, sorry. We want to talk about cholesterol biosynthesis as a continuation of lipid metabolism now. So you said cholesterol is comprised of a core nucleus, and the core nucleus of cholesterol is made up of a hydroxycyclopentanopenantrene nucleus, which is drawn here on the screen. So if you look at the structure of this hydroxyclopentanopenantrene, the ring is, this ring here is the A ring, and this is the B ring, and this is the C ring, and this is the D ring. And there are certain special alkyl group compounds and other functional groups that makes cholesterol stand out in its chemical characteristics. First is the presence of an hydroxyl group on this position. Few number of cholesterol in terms of the carbon position. This will be 1, this will be 2, this is 3, 4, 5, 6, 7, 8. Oh, sorry. 1, 2. This is 2. Yeah, this is 3. Oh, sorry. I made a mistake with the number. Okay, so we start from here. 1, 2, 3, 4, 5, 6, 7, 8, and this should be our color 9, 10. Sorry, this is 10. This is 11. This is 12. This carbon here makes 13. This is 14. This is 15. This is 16. And this is 17. So between carbon 10 and 1, right, there's a methyl group here. And also, there's another methyl group here also. So these are two methyl groups. This methyl group here makes our carbon 18, while this methyl group here makes our carbon 19. And so we have this fused form of isoprenate on the carbon 17. And this is the primary structure of cholesterol. So cholesterol here is usually synthesized primarily from acetyl-CoA. Acetyl-CoA is the raw material required for cholesterol biosynthesis. So what does that inform you? That informs you that for cholesterol to be biosynthesized, there is need for beta oxidation of fatty acid, because beta oxidation of fatty acid is what generates acetyl-CoA. So we need 27 carbons. 27 carbons. I mean, cholesterol has 27 carbons if you count. If this is 19, then this is 20, 21, 22, 23, 24, 25, 26, 27. So cholesterol as a structure has in total 27 carbon components in it. So we look at the steps involved in cholesterol biosynthesis. A moment. let me erase. Okay, to consider the steps that are involved in synthesizing cholesterol, first thing we want to do is we want to make HMG CoA from acetyl CoA, and then after synthesizing HMG CoA, we want to make mevalonate, and then we want to make isoprenoate, and then for isoprenoate you want to make screening, squalene, and from squalene we want to make lanosterol, and from lanosterol we want to synthesize cholesterol. So these are the 7 steps we want to put into consideration. First is to make HMG CoA from acetyl CoA, and then after making HMG CoA, we convert it to mevalonate. And after making mevalonate, we try to form our isoprenoid unit, and then our isoprenoids will condense to form, isoprenoids are 5 carbon. So a lot of isoprenoid units will condense to form a 30 carbon screening, and the 30 carbon screening will eventually form a 24 carbon lanosterol, 24 now. I can't remember anyway, form lanosterol, and lanosterol will then become converted to cholesterol. So let's look at the steps in detail. The first step is formation of HMG CoA. Okay, formation of HMG CoA. How does everything start? We start by, anyway, we take note of the enzyme involved in this reaction. It is the thiolase enzyme. If you remember, what we're talking about thiolase in beta oxidation, and also in lipid biosynthesis, thiolase has the tendency of cleaving, a lysis tendency, and thiolase can also ligate. Do you understand? So yeah, in the active site of thiolase, we have certain amino acids which, okay, now this is what happened. We have the acetyl CoA, which is generated from beta oxidation. Yeah, so there is going to be a cysteine residue in the active site of the thiolase. This cysteine residue obstructs this proton from acetyl CoA, so that eventually we get this intermediate. The intermediate will look like this. Right, with a methylene group. Now this radical that is formed here is then going to combine with another acetyl CoA, Combines with another acetyl-CoA. So don't forget that this carbon here is slightly positive, while this oxygen is slightly negative due to the inductive effect of oxygen. So because of the slight positivity of this carbon, it, it will be attracted to by this lone pair electron, right? And so this is like a cleansing condensation reaction. So we have CH3 like this. Now, if this bond tries to attack this carbon, then it's going to be resonance of, this bond is going to migrate to the top, and so we get something like this. This is our S-CoA, our coenzyme A, and then we have CH2 like this. Now, because of the instability of this charged compound, the bond resonates back, right? And this causes the cleavage of this coenzyme A group. So what is formed eventually will be a compound called acetoacetyl-CoA. We get acetoacetyl-CoA is formed here. And what happens next is that our acetoacetyl-CoA further combines with another molecule of acetyl-CoA. So in a way, we can say that three acetyl-CoAs combine together to form HMG-CoA, right? Okay, we are going to probably formulate an overall reaction for this step, for this process. Okay, so the acetoacetyl-CoA we combine with what? We combine with this charged acetyl-CoA. Of course, we understand how we got the negative charge. And so what happens is, as usual, this negative charge attacks what? Attacks this carbon here. Because there's going to be resonance, and so we get something like this. This is what we get. We get this new compound here. This methyl group here. So I'm bringing it down and so this is O negative, and so this looking at the structure that is binding, that is CH2 or like this, or LCO, right? So this negatively charged oxygen is going to abstract back the proton that has been taken by the cysteine residue in the thiolis. Actually, we are going to get a compound that looks like this. Right. Now this compound will then be treated or acted upon by water. And how does water act on this compound? This is water. It has two lone pairs, so it's richly nucleophilic. So because it's nucleophilic, it acts on this positively charged carbon here, causing this bond to form a negative charge on the oxygen here. And at the long run, we get this product. And we get something that looks like this. The negative charge. Now, if this, okay, let me show you this. Hydrogen, hydrogen. This is going to be positively charged, so it has to lose. This bond has to break so as to balance out this positive charge. And so we have this S correlation. Now this negative charge, because of now you can see negative charge, positive charge. This compound is extremely stable. So this negative charge has to resonate back, and the consequence is going to be the loss of this coenzyme E. And so we get a product that looks like this. The hydroxybutane and the methylbutane and the cysteine and then COO and then OH. And this product here, this compound you have here, is called HMG CoA. HMG CoA is the same thing as beta hydroxy beta methyl butyryl CoA. And why is it called this? The reason why it's called this is because if you look at this is the alpha carbon, this is the beta carbon. In the beta carbon, you have an hydroxyl group, and also you have a methyl group. Understand? So the enzyme that catalyzes this reaction is HMG CoA synthase. HMG CoA synthase, and note that it involves the addition of water to this intermediate, right? So as to cleave this coenzyme A group and CoA group, and so as to give rise to our HMG CoA. So that's the first step in cholesterol biosynthesis, emission of HMG CoA. So the next thing we want to look at is how HMG CoA is transformed or used to form mevalonate. One HMG-CoA is then going to be acted upon by the enzyme HMG-CoA reductase, which is the rate-limiting enzyme in cholesterol biosynthesis. It is the most important enzyme in cholesterol biosynthesis. In fact, it is this enzyme that is targeted by statins, some drugs that are used to reduce cholesterol level. Statins are, let me just write something on statins. Statins are HMG-CoA reductase inhibitors. So statins will inhibit HMG-CoA reductase. You understand? So this next reaction is the rate-limiting reaction, whereby we reduce HMG-CoA with 2 molecules of NADPH so as to generate mevalonate. So what happens is you have your HMG-CoA. This is your HMG-CoA, right? So the first thing first is, don't forget that we're going to reduce it twice. The first reduction step, reduction is catalyzed by NADPH, which always generates hydride. There's going to be some form of hydride release. So this hydride is going to attack this. And then, of course, this bond resonates here. And then we get something like this. And then this is HMG-CoA, and due to the first reduction vacuum, we get meval due CoA, right? So what happens to meval due CoA is, of course, resonance will occur, pushing out this, and so we get a new substance that is now an alkyl, right? This new substance is going to be called mevaldehyde, because it's an aldehyde and alkyl. Now the question is, what happens when you reduce an alkyl? When you reduce an alkyl, it becomes an alcohol, right? When you oxidize an alcohol, it becomes an alkyl. When you oxidize the alkyl, then it becomes carboxylic acid. So we are going to reduce this aldehyde group so as to form an alcohol. Of course, the same enzyme catalyzes the process utilizing NADPH. With this hydride, okay, the negatively charged hydride attacks the as usual, right? So it is going to be response. This will generate some kind of negative charge, which will attract some protons, maybe the proton in water or the proton in acid, in an enzyme. So we get something like this. what do we call this? This compound here is an environment. Environment. And this is the step of generating environment. So environment are generated from HMG code by simple reduction reaction. So we reduce in two steps to form an environment. And the reducing agent that is utilized is what NADPH. The enzyme that catalyzes this reaction is HMG-CoA reductase, and the type of drug that is used to stop HMG-CoA so as to reduce cholesterol level of the blood are the statins. Statins are also called the HMG-CoA reductase inhibitors. Alright, so the next step involves what? Formation of isoprenoids from the environment. New formed environment is to be converted into isoprenoid, right? So this is the carboxyl group. This is our environment. So the enzyme that catalyzes this conversion of mevalonate into an isoprenoid is the enzyme mevalonate kinase. So it's a three-step phosphorylation reaction. So it requires ATP so as to take a phosphate group and phosphorylate this hydroxyl group. So we get this product here that is this way. We get this product here. So this oxygen here is binding to a phosphate group. What do we call this? This is carbon 1, 2, 3, 4, 5. And the phosphate group is a carbon 5, so we call this 5 phosphate mevalonate. So we take our 5 phosphate mevalonate now and further phosphorylate it. In the presence of our enzyme mevalonate kinase, mevalonate kinase, we utilize ATP. This is AD and generates adenosine diphosphate. And so what do we get? We get this product. This will be the okay, let me just let the full structure. And so the second phosphate group also. So what do we call this compound? We call this 5, because there are two phosphate groups. It's not a pyrophosphate. So we call this 5-pyrophosphomethylate, right? So what happens next is that we are going to further phosphorylate this hydroxyl group, right? It depends on the same enzyme mevalonate kinase. So that's to give us our isoprene. The next phosphorylation step is phosphorylating our 5-pyrophosphomethylate. The same enzyme mevalonate kinase, which utilizes ATP generate adenosine diphosphate. So what are we phosphorylating? We're phosphorylating this hydroxyl group here. So we have a product that looks like this. And this hydroxyl group here would have been phosphorylated. Now something special happens here, and it's going to be a kind of cleavage reaction. What will happen is that this negative charge here is going to combine there, and that will cause this bond here to break. So it will resonate in this direction, and that will cause this bond here to break also, releasing this carbon dioxide. And so what do we get? We get a new compound after we've lost this after we've lost this carbon dioxide. Yeah, and you must understand that this next reaction here is catalyzed by an enzyme called what? It's the carboxylase enzyme. So the enzyme is going to be called phosphomevalonate carboxylase. So because we are losing this carbon dioxide, so we form, what do we get? We have this CH2. Now there's a double bond here. So this is the double bond, and then the C, and then this is CH3, and then we have CH2, CH2, and there are two phosphate group. What do we call this compound? This compound is an isoprenate and its name is isopentenyl pyrophosphate. This compound isopentenyl pyrophosphate will undergo some form of isomerization reaction. The enzyme catalyzing the isomerization reaction is isopentenyl pyrophosphate isomerase. So after it is isomerized, isomerism is not too intuitive in a way. It just involves abstraction of the proton from A. Like this double bond shift. One of the protons solvents will be given to this. So we get a new product. The new product that looks like this. Now we have the double bond. CH2H2, then 0PP. So what do we call this? We call this compound dimethyl aryl pyrophosphate. So both this is DMAPP and this is IP. So both DMAPP and IPP, they are both isoprenate. So I'll continue from here into tomorrow with a special grace.